Hello everyone, in this video I'm going to be talking about some basic concepts on mass spectroscopy. I'm not really going to go over too many details. I'm just going to talk about talk enough that you guys know for organic chemistry, especially for sophomore organic chemistry. Not really going to talk too many details. So just to start out with, mass spectroscopy obviously have magnets in there, and it works on the principle that it will have some force, a magnetic force on charged particles. So anytime you have a charged ions kind of going into those magnets or mass spectroscopy, those are the only one that shows up in there. The radicals or the uncharged chemicals don't really show up. So you could have cations and even anions showing up in the mass spectroscopy, but you don't really make anions when you lose an electron. You make cations. So as a result, it's only going to be the cation or the radical cation that would show up on the mass spectroscopy. Now, in order to create a radical cation, which is also called an apparent ion, you must have a beam of electron kind of bombarding this molecule, and you will lose an electron from the molecule that's going to be very loosely bound to the molecule. Now, what electrons are going to be very loosely bound to the molecule? And those are going to be typically your pi bond electrons, or they are going to be your lone pairs, which are also called the non-bonding electrons. However, if you don't have any of those, then it's just going to be the sigma bond, one of the sigma bonds that's going to break up, and it's going to lose an electron. As a result, it's going to make a radical cation. Like in this particular example, I don't really have any pi bond, and I don't have either any lone pairs on it. So I could lose any one of those electrons from any of the sigma bonds. So I'm just going to go ahead and maybe lose this particular one. So you can kind of write it like this. So when you lose it like this, I will have a positive charge here, and obviously you have an electron. So some books may show it like this, where they will be showing one of the electrons, one of the bonds being broken, having only one electron left and the other electron gone, and the molecule will have a positive charge as a result. But some books may show this, okay, I'm going to be losing electron from any of the sigma bonds, so it doesn't really matter which one you pick. So as a result, I'm not really going to show which one I'm really breaking, but I'll show, okay, I'm going to have a radical left, and that radical is going to have a cation, and obviously an electron gone away. So this is how the typical show you're going to have for the creation of a molecular ion, which is also going to be the parent ion. Now, typically this parent ion, or the radical cation that you actually create, is unstable. Now, it's not always true that sometimes it's fairly stable and just kind of stays as it is, but most of the time it's fairly unstable, and it's gonna further break into something, and usually it makes a carbocation and a radical. So I can go ahead and take an example of maybe this guy. I'll just copy this now. So I have, suppose, um, this one broken away, in a sense that this electron that left behind will go on to one of the sides. So then you create a radical here, and then the other guy that's going to be left on the side is going to have a positive charge. So this carbocation that you actually create, it's the one that shows up on the mass spec. This radical is not going to be observed in the mass spec. Now, this carbocation, now how does this really fragmentation going to take place? I'm not really going to talk about the fragmentation into too details in this lecture. I'll have a separate sessions, because the fragmentation really depends on what type of function groups you're really dealing with, and more or less you are trying to make a carbocation that's going to be fairly stable. As long as you can make a fairly stable carbocation, that's going to be the most prominent, or most prominent fragment you're going to have, and that will create so-called in a base peak. So if this is the only carbocation, or the only stable carbocation I can create from this molecule, then this will result in a base peak. Now, what base peak really is, base peak has an intensity of 100%, and the rest of the peaks will have an intensity relative to the base peak. Now, sometimes your molecular ion is indeed going to be the base peak because it doesn't really fragment into anything, but a lot of time whatever molecular ion fragments into and whatever it makes the most stable carbocation, and that will result into in a base peak. And I'll show you some example in the actual mass spec to clarify things. So this is the bottom line of the mass spectroscopy. So remember, you're going to have a charged ion that's going to be passing through the magnetic field. And if you guys taken physics, second semester physics, then you will know how the magnetic field presence and the charged ion can have this magnetic force, and as a result, they will deflect into a particular direction. And you have these deflectors or these detectors kind of on those ranges, and how far it deflects. You based on that, you can figure out what's going to be the mass. So there is obviously a complicated physics and math behind it, but for the organic chemistry student, this is all you really need to know how it really works. Now let's talk about some molecular ion peaks. So you can have M plus. I'll move this a little bit. So you can have something called an M plus cation. So this is also going to be your, obviously, the molecular ion peak, which is also the parent ion. And then you can also have an M+1. I'll talk about what that really means. So suppose this is the mass spectroscopy, the mass spectrum I have for a particular molecule. I don't really know the formula for this, but there are a couple of ways you can figure out the formula, and I'll show you how you really calculate the formulas. But first of all, I want to see the first peak that's in the mass spectroscopy present. And that's going to be this guy right there. And this seems to be at about 86. And then you also have a tiny peak right after this, which is at 87. So this 86 peak is going to be your parent ion peak, which is going to be M radical plus or a radical cation there. On the other hand, the 87 is going to be M+1. Now, where this M+1 really comes from? Now, obviously, we're dealing with these organic compounds here. We have a lot of carbons in there. So carbon exists in three isotopes. So you have carbon 12, we got a carbon 13, and you have a carbon 14. So carbon 12 is about 98.9% abundant, and then you have carbon 13 is roughly about 1.1% relative abundance on this. Carbon 14 is very, very small, and it's so small, I don't even know how small is it. I think it's like 0.00, so many zeros, 1%. So I don't really have to worry too much about the carbon 14, but these are the only two that will really show up. So that's why anytime you have this M plus peak, you're going to have this M+1 radical peak as radical cation peak as well. And this actually does have a very useful information. Now, I'll talk about how you can use this M+1 peak to determine the formula of the compound. But before that, I will show you how you actually predict the formula of the compound if you don't know information about M+1 peaks. So suppose the molar mass of this compound now we know is going to be 86. And I forgot to tell, if you go back and you see a peak at about 43, I would say, this is 43. And 43, the intensity is almost 100%. So this is going to be your base peak. And where the base peak is going to be coming from, it's going to be coming from your most stable fragment that's going to be present in the molecule after you fragment the molecule, obviously, or after you fragment the radical cation. So that also gives you a very useful information. Now, suppose I have 86, or in this case, I have 86 in molar mass, and I want to predict what could be the formula for this guy. So I know I'm going to have carbons and I know I'm going to have hydrogen. So I know carbon's molar mass is about 12 or 12.01 to be exact, and hydrogen is 1.008 or 1 to be, as a rough estimate. So I could technically have, if I say, okay, I got 6 carbons, so 12 times 6, that's going to be 72, and how much we have left out with to get to 86, we're going to have 14 left in there. So 14 hydrogen. So based on that, I'm making C6H14. Now you want to kind of double check the formula if it does really make sense or no. And based on the structure or the compound on alkanes, the CnH2n plus 2, If you have 6 carbons, the max number of hydrogens you can possibly have would be 14, and that seems to be working fine. So one possibility of this formula is going to be C6H14. Now, that does not necessarily mean this is actually going to be the formula, because we don't know other information in the mass spec unless we're given this fragmentation data. Then it's a different story. But I'm not really using the data yet, but I'm just using if you given this mass spectrum only. So first thing, you figure out the formula, you figure out the molar mass, and then you can predict different formulas you could possibly think of. Now, suppose I didn't really take account of oxygens and nitrogen, so what could be the possibilities there? If I have a even numbered mass spec or molar mass, then I'm going to have even numbered nitrogen atoms. So that could be 0, that could be 2, that could be 4, that could be 6, and so on. So that's an even nitrogen rule. So if you have an odd number molar mass, then I will have odd numbers of nitrogen atoms in there. So that could be 1, that could be 3, that could be 5, and so on. So in this particular case, obviously we have 86, so that's an even number. So I could have either 0 nitrogen, so that gives you C14, C6H14, or I could have 2 nitrogens. And I don't know how many nitrogens I really have, but I'm just kind of exploring the different possibilities of these formulas. So suppose if I have 0 nitrogen atoms, then the formula should have been C6H14. But now, what if I have 2 nitrogen atoms? So remember, I can't really have an odd number of nitrogen atoms because it's an even molar mass. So if I have two nitrogen atoms, then one nitrogen atom is 14. So to incorporate 2 nitrogen atoms into this formula, C6H14, whenever you add 1 nitrogen atom, you gotta remove enough carbon and hydrogen so that you will remove a total of 14 molar mass. So I can actually go ahead and remove CH2. So this is something you want to really keep in mind. Anytime you're adding in a nitrogen, you want to remove CH2 from there. So if I add, suppose, plus 1 nitrogen, I got to remove 1 CH2. So in that case, it would have been C5, H12, N. But remember, I can't really add 1 nitrogen because it's an even number, so I got to add another one. So after adding another nitrogen atom, I'm going to have C4, H10, because I'm removing another carbon and 2 hydrogens, and that's going to be N2. So that's another possibility, and you can keep doing it, and sometimes at some point the formula is not really going to make sense. So in this particular case, so what's going to be the hydrogen index of hydrogen deficiency? You can always check based on that. So I got 2 times 4 plus 2, and then minus 10 plus 2 because of the nitrogens there, divided by 2. So that's going to be an index of hydrogen deficiency to be 1. So that's another possibility you have for this formula here. So one possibility you had is C6H14. Like I said, you don't know which one it's going to be, but that's another possibility there. And then what if you add an oxygen atom? So when you're adding oxygen atoms, remember oxygen atoms has a molar mass of 16 or atomic mass of 16, so you gotta remove CH4 in that case. So I have C6H14, and suppose I'm adding 1 oxygen atom, so I gotta remove CH4 there. So we don't really have any particular rule like how many, if you can have odd numbers or even numbers of oxygens. That only applies to the nitrogens. If I remove CH4, then I can have C5, H10O. So that's one possibility. And if I keep doing it, at some point the formula will not make sense. So let's try that again. So it's going to be C4, H6O2. So far it's good. I mean, I could have a possibility of getting a C5H10O, or I could have a possibility of getting C4H6O. Your index of hydrogen deficiency increases as you adding more oxygen atom and as you're removing more hydrogen atom. So in this case, the index of hydrogen deficiency, and I expect you to know how to calculate that. If you don't know, you may want to watch another video that I have posted on how to calculate these guys. So this is going to be 12 minus 10 divided by 2. This is going to be 1 index of hydrogen deficiency. That means there's going to be either a double bond or there's going to be a ring in there. And this particular one is going to be 4 times 2 plus 2 is 10 minus 6. So it's going to be 4 divided by 2. So index of hydrogen deficiency here is going to be 2. So that's okay as well. As long as you're not getting a negative index of hydrogen deficiency, you should be okay. So these are some of the possibilities of these formulas I could have. Now, how do I really know what particular formula I have? They would have to actually tell you that there is actually an oxygen atom, or maybe they'll give you an IR where you can look up the function group. But suppose if you are given this mass spectrum data, then based on the mass spectrum data, you can actually calculate what's going to be the formula. So that's the benefit of having the mass spectrum data. So I'm going to be focusing on 87, and we're going to be focusing on 86. 86 and 87, these are the percentages for those. So remember, this 87 is going to be M+1, and 86 is M plus radical there, a cation radical. So the first thing I need to do is divide those. So 1.2, that's going to be their relative height of the peak, divided by 20.9 times 100, and see what that gives you. So that's 5.74%. And then I know I said earlier that the carbon-13 is 1.3 relative abundance in nature. So I can go ahead and take 5.74 divided by 1.1 and see what that gives you. So this is a technique that's really useful if you're given these relative height ratios. If you're not given that, you're going to have to do the long way just I did earlier. So divided by 1.1, so that's going to be 5.2. So that tells you this is how many carbon-13s you have. And if you have that many carbon-13s, that's how many carbon-12s you're going to have. You're not going to have like different numbers of carbon-13s and carbon-12s. It's just that their ratio is going to be staying constant for this particular molecule. So if you have 5.2, obviously you can't really have fraction numbers of carbons. I can round it down to 5. So if I have 5 carbons, then I got to figure out how many other hydrogens I could possibly have. So if you have 5 carbons, so 5 times 12 is going to give you 60. And to get to 86, someone is going to be like, okay, I got to have how many hydrogens? I got to have 26 hydrogens. So C5H26, is that possible? Well, that's not really possible because if you have 5 carbons, the max number of hydrogens you can have with 12. So that means you're getting a lot of hydrogens there that you don't need. And that's when you guys start thinking, okay, what if I add an oxygen atom? So if I add an oxygen atom here, then I gotta get rid of um, 14 molar mass. And then typically, if I want to get rid of 16 molar mass rather, or atomic mass, if I want to get rid of 16 atomic mass, what do I have to do? Either I can remove a 1 carbon and 4 hydrogens, but if I see here that I have so many hydrogens that I need to get rid of, so I can probably just get rid of 16 hydrogens there. So that's going to make C5H10O. And if you go back down here, we actually did have that formula explored before that. So that, that was a possibility there. So this is how you're going to be calculating based on your relative height. So always take the ratios of M+1, so M+1 radical cation over M plus radical cation times 100. And then whatever answer you get, you divide that by the relative abundance of carbon-13, which is always going to be 1.1. And that roughly tells you how many carbon you're going to have. And based on that, you can predict how many hydrogens and maybe nitrogens and some other stuff you're going to have in the molecule. So that was about M plus and M+1. Sometimes you may have M+2 radical cation, and they will give you very useful information. So in this particular molecule, let's focus on these parent peaks or the molecular ion peaks. So one of them is actually at 108 and the other one is at 110. And if you see here, you do have M+1 here as well. So that's something you want to keep in mind. So that was M+1 radical cation. 108 would be M plus radical cation, and 1010 is M+2 radical cation. Now, where would they really show up? And this is going to be very useful when you're taking organic chemistry during this mass spectroscopy, especially when you have alkyl halides. So you have a bromine and a chlorine that typically show the M+2 peaks, but in different ratios. So if you have a bromine, bromine has two isotopes, bromine 79 and bromine 81, and those two isotopes happens to be almost 50% and 50% relative length, or sometime I would say one of them is like this one is almost 51% and the other one is 49%, but roughly 50%. And as a result, this these peaks of 108 and 110, their relative height is almost equal to one another. So that tells you you got to have a bromine there. Okay, and then you can double check that by looking at the peaks at about 79 and 81. So you got these tiny peaks that shows that you got the bromine there. So if you lose, suppose you have 108, so 108 is coming from 79, obviously. So if I subtract 79, so how much you gonna have left there? So I'm gonna have 29 left. So if I have 29 left, and if you go back here, your base peak is indeed at 29. So that means after losing the bromine, you make your most stable fragment, and that's going to be at 29. And what really shows up at 29, it's a typical cation that is really going to show up at 29 would be the CH3, CH2 cation. Because if you add up these masses, carbons are 12, so that's 24, and plus 5 hydrogens, that's going to give you a total of 29. So that tells you this is actually going to be CH3, CH2, Br. So if you have a bromine, it's probably going to be one of the most easiest to recognize because their parent ion peak will show M plus and M+2 radical cation in almost equal amounts. So their peak ratios is almost going to be equal to one another. What about if you have chlorine? So chlorine ratio of isotopes is not 50-50, but rather it's almost, so you have chlorine 35 is about 75%, and chlorine 37 is about 25%. So you can say chlorine 35 is about 3 times more abundant than the 37. So if you see your M plus peak and M+2 peak, the M2 plus is actually 3 times shorter. That's because chlorine 35 is 3 times more abundant than chlorine 37. So anytime you have an alkyl halide that has a chlorine atom in there, you're going to see two parent ion peaks where M plus radical and M+2 cation radical, where M plus cation is going to be 3 times more in height than the other one. If you come down here, um, if I see this peak right there, and that's going to be at 77, and if I subtract, so this is supposed to be at 112, seems like. So it's 112 minus 77, so how much we have there? So I get 35, so that means I am losing 35, which is actually the chlorine there, so that tells you that it's going to have a chlorine atom in there, and then you can figure out what's going to be the 77 and just kind of give you an idea. The 77 typically is going to be your benzene ring, because benzene itself is 78, but then seems to be there's a chlorine there. So once you lose this chlorine, you make this fragment, the phenyl fragment, and that's going to show up at 77. So that's how you know this is going to have chlorobenzene in there. But I'm not really worrying too much about the fragmentation in this topic. I'm just going to be showing you most common patterns of these mass spec. What if you have two bromines? Then what happens? So things kind of changes a little bit because we have two bromine. You will start seeing M+2 radical cation and M+4 radical cation. And what's going to be their relative height of the peaks? So I have this molecule that has two bromines in there, and you know I have bromine 79 and bromine 81 as their isotopes. So when I do the combination there and look at the probabilities, I see um, bromine 79 and bromine 79 coming one, so that's going to make an M plus peak. And then I see bromine 79, bromine 81 here. Then I also see bromine 81 and bromine 79 here. Then I'll see bromine 81 and bromine 81. So if I focus on these two guys right there, so bromine 79 and bromine 81, that comes in twice. So that means your M+2 peak is actually going to be 2 times bigger there. So that's why you have this M+2 peak is twice the height of the other one, because bromine 79 and bromine 71 has a probability of taking place once, and bromine 81 and bromine 81 also has the probability of taking place once. So that's why this is going to be 1 to 2 to 1 ratio of these peaks height. So this is how you're going to be determining, and you can obviously calculate the chlorine as well based on their data and their relative abundance as well. So this is how you're going to be looking at the mass spectroscopy, very basic stuff.